Okay, good morning. Today we move the chapter to the sixth, and the topic is related to the momentum equations. So, this is a slide shows the key concept for this chapter. As you can see, the sentence showing here, engineers design systems by using the momentum equation. Okay, so what's the momentum equations? As the words showing here, the first item we need to know what is the external force and what is the momentum flux. And finally, we will introduce the differential form for the momentum equations, which we call that is the control equations of the flow field. Okay, as we teach in chapter 5, the final part, we will introduce the differential form of the continuity equation. So for this chapter, we will have the same ideas. We will also introduce the differential form of the momentum equation. Okay, so the most important thing idea is we will have the external force. Okay, and then we have two conditions is equal to 0 or not, and then we will have the momentum flux and along the control surface. So we will have the momentum flux and related to the control surface. Okay, so the slides summarize all of the learning outcomes in this chapter. Because we discussed the external force, so we will very quick brief introduction about the Newton's second law, because the Newton's second law is associated with the force, and then we will introduce the linear momentum equations, and also introduce the angular momentum equations. So in the following class, you will know what is the significant difference compare the linear and the angular momentum equations. And a lot of the difference in this chapter compared to chapter 5 is, in this chapter we will have some case the control volumes is moving, so we call that the moving control volume. Okay, so first we discuss with the force, and our topic is how can we distinguish the force between the body and the surface force. So the slide showing here is one example. Our target is airplane, and there are four forces we can see, such as the lift force, and the thrust force, and the drag force, and the weight. Okay, and the different force we will have the different directions of the force. And how can we distinguish the force between the body and surface force? So there are providing us certain definitions. As we can see, the surface force, the force that requires physical contact or touching between the two interacting bodies. But the body force that can act without the physical contact. So the very important is, if we would like to distinguish the force between the body and surface, the surface we need the contact and the touching between two interacting body, but the body force without the physical contact. So the slide just summarize all the force related to the body and surface force. So the left hand side, because the body force not require the physical contact, so the example related to body force. Showing here are magnetic force, is electric force, and the gravity force. And the right hand side just list the surface force, and if we looking for the force related to the fluids, and there are 7 important force. The first one is the pressure force, second is shear force, buoyant, lift, drag, surface tension force, and thrust force. Okay, so as I remember, we have teach the very important 7 force in the chapter 2. So all of the significant force associated with the fluid are the surface force. Okay, so what's the Newton's second law? As we know that the external force showing here, okay, it will equal to the particle mass multiplied the acceleration. So we know that if the directions, we fix one direction if the sum of the external force equal to 0, and the particle is under moving, and then its moving speed is constant if the sum of the force is equal to 0. But if sum of the force are not equal to 0, that indicates we have the additional acceleration required for these directions. So again, if we see the example of the airplane, and then we can see we have the lift force showing here with the angle between the vertical line theta. So we know that the lift force can project into the directions normal to the path. So we project the direction normal to the path, and then we have the additional force along the directions normal to the path. So we have the additional acceleration normal to the path. We call that is AN showing here. Okay, so that's the idea. We need to identify sum of the external force is equal 0 or not. If not equal 0, that indicates along this direction we have the external force. Okay, so the slide just summarizes the step. How can we visualize the conditions for our force balance? And then we call that is the visual solution methods. Okay, so the idea is first we draw the diagrams of the force. So we can draw the force diagram first. So we have the force diagram, and because the force is the factors, so the second step, and we will divide the factor to the scalar. So we need to know the scalar directions. So in here we have the x directions, and another direction is the y. So we will convert the force into the scalar directions, x and y. So in here we know that we have the lift force, and then we have the theta angle in here. Okay, and then we will project the lift force into the sine. Sorry, here the theta is not. There is the theta. It's angles with the vertical line. So we will use the sine theta related to the I direction is x, and the cosine theta related to the j directions. And we have the additional force contributed by the airplane weight. So we have an additional weight direction related to the j direction. And then finally, we only have the acceleration items is the an. So we have the an acceleration for the airplane particle with the I directions. So finally, we can divide the vector equation to the scalar. So the vector to be the scalar equations, we only focus on the x directions and the y directions. Okay, and then we can discuss with the force balance. So the second, for the y directions, we don't the sum of the external force is equal to 0, so we don't have the acceleration along this direction. Okay, but for the x directions, we have the external force, so the accelerations will occur along the direction normal to the path. Okay, so the next one, if the left hand side and the right hand side are the vector equations, so usually we will draw the diagram each others, and then we just make the balance for the same directions. As you can see, for the x directions, we have the x2, x3, and we need to project the x4 with the cosine theta to be project to the horizontal direction, but with the negative directions. So you can see the negative in here, and will equal to the right hand side factors. We have the y1 along the x directions, and we need to project the y2 with the cosine theta 30 degree, and we have the x directions contributed by the y2. Okay, so and the second one is related to the y directions. So again, you can try by yourself. So this is the slide just show the idea if the right hand side and the left hand side are the vector equation, so you can make the balance. So the first one, you need to sketch the diagrams and write to the reduce the equation to the scalar from the vector. Okay, so the Newton's second law, if we consider the system of the particles, as we mentioned before, this chapter we are discuss with the relationship between the external force and the momentum flux. So I can we know that the sum of the external force will equal to the momentum changes with the time, and this is related to the momentum changes in the closest systems. Okay, so as you can see, first we can what is the momentum? The momentum is related to the particle mass multiply the v velocity, right? And because the velocity with the different directions will have different contributions of the external force. So the force are the factors, and the momentum and the velocity are also the factors. And then if we consider the systems with include the many fluid particles, so we need to use the sum of the mi. The different I particles have the different I velocities, and we sum all of the moment in the systems. So we call that is the total momentum of the system. Okay, so since we know that the key knowledge is we have the external force related to the momentum changes in the closest systems. So if we go back to remind, we have the transpose nano transpose theories. We know that the dB dt in the closest systems. Here the capital B is the extensive properties will equal to the d and dt. Then integrate the control volumes with the small b is the intensive properties, rho and the dv, plus the integration along the control surface, the b, and still have the density rho. And we have the factors dot product with the small cross-section area factor. Okay. So because we are discussed with the momentum changes with the time, so here the extensive B, we know that it is the momentum. And we know that the intensive property will divided by the extensive property divided the mass. So we know that the intensive property will to be the velocity. Okay, so we can go back to see the nanotransport equations. The dB will replaced by the dN, and dt will equal to the d and dt integrate along the control volumes, and the b is a small the factor velocity, and the rho and the dv, and plus the control surface and the v velocity factor, rho factor v velocity dA. Okay, so this is we call that the equations, the linear momentum equations. And then we know that the total momentum change with the time in the cross system will equal to the external force. Okay. And here I highlight some very important. I use the capital velocity and the small velocity v to indicate the different velocity. As you can see the sentence showing here, the capital V showing here is the fluid velocity relatively to the control surface. But the small velocity V showing here is the fluid velocity relative to an inertial reference frame. So they are the difference, and in the following class we will discuss how different they are when we consider the moving control volume problem. So we will discuss for the difference compare the velocity showing here, especially for the moving control volume case in the following class. Okay, so sometimes we have the integration problems, but if we assume the flow velocity is the uniform flow velocity, and then for the integration problem in here, the V, we can take the outside of the integration operator. So only the inside showing here, this is equal to the MCV, right? So our equations integrate with the along the control volumes will to be the dmCV and the VCV and the dt. And then for the case for under the control surface integration, we also can take the constant velocity outside, because we assume the flow velocity is a uniform flow. So we can distinguish the integration part into the outflow rate minus the inflow rate, and multiply the outflow velocity and the inflow velocity. So because we assume the uniform velocity, and then we can convert the integrations operators into the summations. Okay, so this is another formulas for the linear momentum equations. So sum of the external force is equal to the mcv vcv change with the time, and the plus the momentum change caused by the outflow part, and another is the momentum change caused by the inflow part, and there is the minus in here. Okay, so today we may stop here, and then we have the quiz. So before the quiz, I just